Welcome back everybody to our second lecture in Unit 4. And today, what I like to think we're talking about today is more transducer anatomy. So we're going to shift a little bit away from all those formulas and all those physical principles. And we're actually going to talk about how our transducer is constructed. And then we're going to talk, we're going to get back to the physical principles about the transducer a little bit in this chapter as well. So really what we're going to really be focusing on is a very basic transducer. So when we think of the transducers that we use now for our diagnostic medical imaging, they are so complex. They've got tons of little itty bitty crystals that sit right at the face of the transducer, like hundreds of them. And then there's these really complex electrical components that are in there to make all those little crystals work and to receive the echoes coming back. And it's just such a sophisticated piece of instrumentation. We're going to break it down to like 1970s transducer. And by learning about these really, really simple transducers, you'll have a basic enough understanding of how your transducer that you hold in your hand, how that transducer is working. So remember, we're doing super simple basic just to understand the concepts. It mostly applies to what is going on in current transducer modeling, but remember our current transducers are so complicated that we're just scratching the surface. So with that, let's go ahead and get started. So what is a transducer? Well, we know that transducers are a device that converts one form of energy into another form of energy. And so when we think about car engines, you put gasoline in and it turns it into kinetic energy. So we have chemical energy being converted into kinetic energy. Humans, we eat food and then our muscles do things and they move us. So again, chemical energy into kinetic energy. And so transducers are the same thing. They get electrical energy and they make it into sound energy. And then sound energy comes back and that gets transformed again into electrical energy. So transducers are anything that convert one form of energy into another, and that's 100% what our transducers are doing. Remember, it's electricity and sound being converted to one another. And the way that that conversion works is through the piezoelectric effect. So the piezoelectric effect is a material's ability to create a voltage when deformed. And then we have a concept also known as the reverse piezoelectric effect, and this is a material's ability to create a pressure wave when electricity is applied. So let's think about this and how this is for our transducer. We have a transducer, and again, I'm going to draw very simple drawings here, hopefully. And at the front of our transducer, all these little piezoelectric crystals. And each one of these crystals has this wire that connects back to it. And all of these wires head back to the machine. And so during transmission, grab another color here. So I'm going to do T for transmission. Electricity is coming down these wires. And when the electricity hits our crystals, what comes out is a sound wave, right? So what does that line up with? Let's go back to this. So electricity comes in and sound, which we know is a pressure wave, a mechanical wave, is created. So during transmission, we get the reverse piezoelectric effect. All right, so transmission is electricity being converted into sound during transmission. Now when we think about what happens during reflection or reception, now that sound wave is coming back, right? And it's going to interact with the crystals, and that's going to create electricity back to the machine. So during reception, we have sound being converted into electricity. Those are lightning bolts, if you didn't know. Those are awful lightning bolts. So now our reception is the true piezoelectric effect. So remember, during transmission, when sound is being sent into the body, it's the reverse piezoelectric effect. And during reception, it is the true piezoelectric effect. So how do we get a piezoelectric material? Piezoelectric materials are also known as ferroelectric, and they can be made of natural materials. So quartz and tourmaline are both natural rocks, natural materials that have piezoelectric properties. Again, remember that means when it is deformed, that another energy comes out of it. And we usually talk about electricity to a pressure wave. Let's go back to the whiteboard real quick here, just so I can draw that out for you. So when we start, we have this kind of a crystal. Let's see if I can draw this. We have this crystal here, and electricity comes into it and interacts with it. And what happens is that that crystal kind of bends in on itself, it deforms, and when it deforms like this, that sound wave or that pressure wave comes out of it. And then the reverse is true. When we have our sound coming back, the sound wave comes back from it. This is already deformed. It's going to kind of pop back the other way, and then electricity will come out of that. So piezoelectric materials deform when they interact with electricity and pressure waves. And we can find those naturally in the environment, quartz and tourmaline. Now, man-made materials can also be piezoelectric, and the one that we use for ultrasound are called lead zirconate titanate material. And that's abbreviated down to PZT. And that is from the chemical symbol for lead being P, zirconate for the Z, and then the titanate gets the T. So PZT is what you'll often hear our crystals called, PZT crystals, PZT material. They also are called the ceramic, the active element, or crystals. So along the face of the transducer, we have these man-made materials, these PZT crystals, that interact with electricity from the machine and put out sound, and then interact with the reflections coming back to make electricity that gets sent back to the machine for processing. In consideration of what to use for PZT materials, many manufacturers are going to use these man-made materials. That's because they can make them perfect. There's no marks within them. They can be made and cut to the perfect size, and it just results in better imaging. So no, we don't use quartz and tourmaline for our transducers. It's always been a man-made material, but this quartz and tourmaline do have the same qualities. So when we look at the basic transducer construction, remember I said we are talking about such an elemental transducer configuration here, to the point where we literally only have one PZT crystal. Okay, and it's a thing. When transducers were originally made, they used to have one PZT crystal. It used to be disc shaped, and we'll learn about that in chapter 12. Anyway, so we have our basic transducer construction. We're going to go over each of these bits in detail, but the first outer part on our transducer, this is called the matching layer. And the matching layer sits right in front of the PZT crystals. So the matching layer has a couple duties, and then the PZT crystals sit behind it. And this is where the sound is going to interact with the electricity that is coming in from the wire. So the electricity comes in from the wire, interacts with the PZT. Matching material helps, and we'll learn about that in a second. And then that heads into the body. Now what's around these components is also very important. This kind of purple area is called the backing layer, and the backing layer helps to keep the PZT crystal from ringing a long time. And we're going to learn too why this is important, that we have a backing material in our imaging transducers. The other things that sit around these materials, we have the acoustic insulator. So the acoustic insulator keeps all the sound energy created by the transducer in the transducer, where the electrical shield is going to protect outside stuff coming into the transducer. And then lastly, we have the housing or the casing, which is that plastic part that you hold on to when you're scanning. So let's take a look at each of these components in more detail. So first we'll talk about the matching layer. And what the matching layer does is reduces the impedance difference between the PZT crystals and the skin. So remember back to chapter 6, we talked about impedance. And when there's a big impedance difference, we have big reflection. And so if we have a large reflection, that means we can't get a lot of sound into the body. And if we can't get sound into the body, then we're not going to get images, right? So we need a material that helps move the sound from the PZT crystal into the body. So the PZT crystals have an impedance that's 20 times greater than skin. So this matching layer is placed in between to create less impedance from the PZT crystal to the matching layer to the skin. A second thing that we put in between the transducer and the skin is our gel. And remember, our gel is water-based. Remember, water-based things have very low attenuation. And so that is going to, again, act as another conduit to get the sound into the body. So if we think about it, we have our transducer, and then we have our matching layer right at the face of the transducer. Our PZT crystals are back here. And then this is the skin that we are imaging on. If we just did PZT crystals to skin, most of that sound is going to get reflected back. Very little is going to go through. And because of that, we'll have lots of attenuation. We won't get our diagnostic images. Now that we have the matching layer in there, most of that sound is going to continue through with a little bit coming back to the transducer. And that's why we get some kind of fallout, speckly stuff right at the top of our screen. We also know that air likes to scatter sound. So if the sound were to come out and just hit this air that's here, we're going to get sound going in all sorts of directions. Again, very little actually going into the skin. So we use our gel. Now we have this layer of gel in here. There's no air, just this water-based gel, and that's going to make most of our sound go right into the body. So that gel helps us to direct the sound into the body. It has a similar impedance to the skin. So again, we're matching impedances through these layers as best as we can to get the most amount of sound into the body. The matching layer then is going to be a calculated thickness, and the thickness of the matching layer has to do with the frequency of the transducer, because we know that frequency affects the wavelength. So the matching layer is 1/4 the wavelength of the frequency of the transducer. So now we're looking at the PZT material, the crystal that sits behind the matching layer. And remember, it changes shape when pressure or electricity is applied. So during transmission, electricity comes in, changes the shape, sound comes out. When sound comes back, it changes the shape again, and electricity comes back into the transducer. Remember that it has multiple names: PZT crystals, active element, the ceramic, the active crystals. I usually just refer to it as the PZT when we are talking in physics. The PZT crystal also has a formula that we need to know, again related to both the frequency and the wavelength, and it is half of the wavelength thick. So if you think back to what the wavelength formula is, we know that it is wavelength equal to 1.54 millimeters per microsecond divided by the megahertz, the frequency, right? And this is for soft tissue. This is once the wave has traveled into the body. So it's a little bit trickier to necessarily calculate out what the wavelength should be of the PZT or of the matching layer, because the speed through these two materials is different than this 1.54. But if we just kind of want to throw caution to the wind and use our 1.54, say we had a 3 megahertz transducer, and we'll just use our 1.54 because that's the formula that we have for figuring out wavelength. We know then that our wavelength would be about 0.5 millimeters. So if our wavelength is 0.5 millimeters, then our PZT crystal is half of that, and our matching layer is 1/4 of that. So 0.25 and then 0.125 millimeters. So PZT, matching layer. And I was thinking really, really hard about what would be an awesome way to remember. Half is PZT and 1/4 is matching layer, and I honestly did not come up with anything good. I wish I had better news for you all. So if you guys know of anything, I think that would be an awesome hint or trick to post in our assignment. What helps you remember that the formula for PZT is half the wavelength, and what is your trick for remembering that 1/4 of the wavelength is for your matching layer. Moving on, then we have the backing material, and the backing material sits behind the PZT crystal. And the whole job of the backing material is to dampen the sound wave to stop it from ringing for too long. We know that short pulses improve our imaging. So a short sound wave is going to be better. The amount of backing material is going to be different for each probe, and it depends on the function of the probe. Now we talk about diagnostic imaging because that's what we're doing. That's what we're learning about, right? There is also ultrasound being used to test building materials. You can use ultrasound to be therapeutic. And we've already learned that continuous wave ultrasounds don't produce images, but we can still use them to assess biological, arterial and venous function. So, with that being said, backing material is very important for imaging purposes because they create those short sound waves. Backing material is not necessary for a continuous wave. It's not necessary for therapeutic. It's not necessary for industrial use of ultrasound. So again, it depends on what your ultrasound purpose is if you're going to have backing material and the amount in it. And I just want to highlight a little bit more. We talked about continuous wave, right? We have our continuous wave. This cannot create an image, right? Because there's no off time. So then we learned about pulse waves, and we know pulses come out, we have that off time, and then we have another pulse. With that backing material, what we end up getting are these like little chirps, and then lots of listening time. Little chirp, lots of listening time. And that backing material is going to create those short pulses, which is better for imaging. So that's why we have that backing material. Now the next part is the power supply, and I called it the wire earlier, and that's because it's bringing electricity into the transducer, and then it's going to bring the electrical impulses that come back out of the transducer and back to the machine. Now this example of our transducer is correct because we have our wire coming in. This is what would be connected to the machine. It's going to go in through the transducer. There's one wire within the housing of the transducer connecting to this one PZT crystal. So this is a channel. It is the one PZT crystal, the one wire, and then in the machine there's an electronic component that this one wire is going to connect to. That being said though, on our current transducers, we have 256 crystals on the face of our transducer. That means that there are 256 wires running through that cord that go back to 256 electrical components in the machine. Each crystal has its own itty bitty tiny wire. And that is why it is so important that we really take care of our cords, make sure that they're not on the ground, that we're not rolling over them, because one of those wires gets damaged, that means one of our crystals is damaged. And as our crystals get damaged, it degrades our pictures. So a channel is going to consist of one PCT crystal, one wire, and a machine electronic component that it connects back to. That wire then is responsible for bringing electricity in and bringing electricity back out for processing. The next layer out is the acoustic insulator. That again keeps electric energy and sound energy within the transducer from affecting the acoustic elements. So there's electricity coming in through the wire. There might be some extra ringing and pulsation once it hits the PZT crystal, and maybe the dampening or backing material can't collect it all. So the acoustic insulator is going to absorb even more of that, because we know that these PZT crystals are very sensitive to pressure changes or to electrical changes. And so we want to absorb all the extra things that we don't want, that are not included in our diagnostic information, so it doesn't ruin our picture. The acoustic insulator is usually made of rubber or cork, something that will absorb energy very easily. The electrical shield then is the next layer out. This is usually made of metal, and it's very, very thin. And the job of the electric shield is to keep outside electricity from coming in and affecting our PZT crystal. Now, outside electricity might be energy from surgical instruments, it might be energy from other electrical machinery in like ICU rooms or something like that. We want that extra energy that's out in the world to not get into our transducer, so it again does not affect what's happening inside and ruining our picture. We only want our diagnostic electrical impulses and sound reflections. And then the last part is the housing or the casing. It's that plastic part that holds all of the components of the transducer. And this is a very important piece. This is what keeps the patient from being shocked, from you being shocked. So it's very important that we inspect the housing or the casing for any cracks. We want to make sure that it is intact. If it is not, then you need a new transducer. You should not use any broken transducers on a patient. So we're going to kind of circle back to a few of the components that we talked about and talk about a little bit more detail than what we have discussed. And I already kind of alluded to some of it, so we're going to just go a little bit more in detail on some of these concepts. So the matching layer we talked about changes the impedance between skin and the PZT, because if we were to put the PZT crystals directly on the skin, a lot of that sound energy is not even going to make it in. So the matching layer sits in between, so we can have a smaller difference of impedances between the PZT crystal and the skin. Remember, when we have large impedances, we have large reflection. So we want little impedances so we can get most of our transmission into the body. So if we look at those layers that we were talking about between the PZT matching layer, gel, and skin, this is the order that they would go in, from largest impedance down to the lowest impedance. And so again, we're just kind of using smaller increment changes of impedances so we can get more transmission into the body. Backing material, we talked about that it keeps the pulse from ringing for a long time. Remember, continuous wave rings for super, super long, lots of ringing. No images come from that. So the shorter the pulse, the better our images are. And what that improves is the axial resolution. And I believe next unit we'll talk about axial resolution. So we'll learn more why short pulses are better. When we don't have any backing material, we get those long pulses, those long continuous waves. And when we have those longer waves, we have poorer images, again, due to axial resolution. I guess just as a idea of what we're talking about with axial resolution, if this is your transducer and this is your pulse line that's coming down, you're going to have reflectors along that line that are parallel to how the sound is coming into the body. And your reflectors need to be at least that pulse apart. They need to be the wavelength apart. The pulse apart, excuse me. So as that pulse comes through, it's going to move down, and if those reflectors are separated out at least by one pulse, then you'll get two reflectors on your screen. But if you have two reflectors that sit within one pulse, then only one reflector is reported on the screen. So axial resolution, shorter pulses, gives us a better chance of seeing more detail in our image. Again, we'll talk more about that in detail when we get to it. So our backing material should be able to absorb sound well, and it's actually going to have a similar impedance to the crystals. So when they are activated, the sound is going to be more likely to transfer into the backing material versus being reflected from the backing material. When we use backing material in our transducers, there are three consequences that you need to know. The first one is that it has decreased sensitivity. The second is that it creates a wide bandwidth. And the third is that it has a low quality factor. So let's take a look at each of these a little bit more in detail. So decreased sensitivity means that the machine is going to be less sensitive to weak echoes that are returning from the body. So that dampening is actually going to occur on both sides of transmission and reception. And we know that the echoes coming back from the body are very, very weak. And so they're going to become even more weak once they interact with that backing material during reception. And because of that, then we might lose some information or some echoes from the body. So again, if this is our transducer, our PZT crystal is here, and then we have our backing material here, our wire coming back. So this is the rest of our transducer. Okay, so during transmission, electricity comes down the wire, interacts with the PZT crystal. Some of that sound is going to get absorbed by the backing material, and that little pulse is going to come out. During reception then, our sound waves are coming back, right? It's going to create an electrical current into the transducer. Some of that will be absorbed by the backing material, and then some will continue on through the wire. But these are really, really weak echoes that are coming back. So we're going to get really weak electrical voltages out of here. And if the backing material absorbs a good chunk of that, then what actually makes it into the wire and back to the machine is going to be very tiny. And because of that, the weaker these echoes are, the weaker our final electrical voltages, and that makes sense then why we would be less sensitive to those very weak echoes. So backing material reduces the sensitivity of the transducer. The second consequence then is a wide bandwidth. And bandwidth is actually pretty awesome for ultrasound. So bandwidth takes into the fact that each transducer has its own what we call resonant frequency. And a resonant frequency, if a transducer were to send out just one frequency, that would be its resonant frequency. It'd be a very pure wave. What happens with the backing material, though, is that the backing material kind of puts a damper on everything, and it changes how the wave is produced. So again, we have our transducer. No backing material, it would just ring, 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 ring. Beautiful tone all the way out. It'd be one pure, we'll just say 5 megahertz. But now, with our backing material, again, we have that backing material here. Instead of just ringing forever, we get these little chirps, and they actually have kind of a weird profile to them. They have multiple frequencies within the chirp. And so now we are no longer getting a pure 5 megahertz tone. We're getting this weird chirp that has anywhere from maybe 1 megahertz to 7 megahertz. So pure ringing creates pure tones. Chirps have multiple frequencies within them, but that's good for us. That's good for ultrasound. So if you've ever listened to your transducer, sometimes you can actually kind of hear it. You'll hear this like, those are those little chirps that are coming out, and we're catching a few of them that we can actually hear. We're clearly not hearing what's going into the body because it's ultrasound, but it kind of gives you an idea of how those like little chirping noises sound like. And again, those little chirps or clicks are going to have multiple frequencies within them, both above and below that resonant frequency. So you'll often see on our transducers, a lot of them are listed like a 12.3 or a 9.3, a 12.5, 5.1. Those are listing the bandwidth or the range that that transducer produces. Very rarely are you ever going to see just a transducer that says 3 megahertz. Those are going to be continuous wave transducers, because remember, continuous wave transducers don't have backing material. We want those to ring on and on and on because they're creating continuous waves. So those ones are going to have just that resonant frequency listed, 3 megahertz, 7 megahertz, where our imaging transducers usually have a bandwidth or a range of frequencies listed. So to figure out bandwidth, we would take the max frequency that a transducer can create and subtract the minimum frequency that a transducer creates, and that is our bandwidth. So for example, very common transducer that we have is the linear 12.5. So we would take our max, subtract our minimum, that means the bandwidth is 7 megahertz. Simple enough. So just another example, if our maximum frequency is 7 megahertz and our minimum frequency is 4 megahertz, then 7 minus 4 equals 3 megahertz of bandwidth. Wider bandwidths are going to be associated with our imaging transducers. Narrow bandwidth is usually, again, with therapeutic or continuous wave transducers. The third consequence of having backing material then is low Q factor. So the Q factor refers to quality factor. And quality factor is a unitless number that describes the transducer's main frequency and how it relates to the bandwidth. So the Q factor formula then is the main frequency of the transducer divided by the bandwidth. So here's an example. We have a transducer A that has it's a 5 megahertz transducer. So that's its main frequency, that's its resonance frequency. And it can emit frequencies up to 8 megahertz and down to 2 megahertz. That means that the bandwidth is 6 megahertz because we're subtracting 2 from 8 to get the 6. And then the Q factor will be 5 divided by 6. Our second transducer is a 3 megahertz transducer but emits frequencies up to 4 and down to 2 megahertz. The bandwidth on this one is 2 megahertz and the Q factor is 3 divided by 2 or 1.5. So let's head back to the whiteboard to take a look at these examples again. So we have our transducer. It's a 5 megahertz transducer. That is its resonant frequency or its main frequency, but it can emit up to an 8 megahertz and down to a 2 megahertz. So remember, to figure out bandwidth, we are subtracting minimum from maximum. So 8 minus 2 equals 6 megahertz for our bandwidth. Q factor then is going to be our main frequency divided by our bandwidth. So Q factor will be 5 divided by 6, which equals 0.8. Remember, Q factor is unitless. There are no units for it. Let's take a look at that transducer B then. So transducer B is a 3 megahertz transducer. It can emit up to 4 and down to 2. So the bandwidth again is going to be 4 minus 2, which equals 2 megahertz. The Q factor then is going to be the main frequency divided by the bandwidth. So 3 divided by 2, which equals 1.5. Let's take a look at one more that's not on your sheet here. Let's say we have a continuous wave transducer that has a frequency listed as 7. It can emit up to maybe like a 7.25 megahertz, and maybe it can go down to maybe a 6.75 megahertz. Maybe it doesn't have much of a range. It usually is going to operate at that very pure. So 7.25 minus 6.75 equals 0.5 megahertz of bandwidth. That's very, very low, right? And then we're going to divide 7 by 0.5 to get our Q factor, which equals 14. Now look at our Q factor for our continuous wave example. Super high Q factor, right? A little bit smaller difference equals in a moderate Q factor, and then a very wide bandwidth results in a very low Q factor. So let's go back to the slides and see what that means. So our example showed us that our imaging probes that have backing material are going to have a wider bandwidth and a low Q factor. That's going to be more like transducer A. Transducer B is probably closer to a non-imaging probe, and that last example that I showed you with the continuous wave probe is definitely a non-imaging probe. So they don't have any backing material. They're going to end up with a lower bandwidth and a high Q factor. So low Q factor is associated with backing material. High Q factor is associated with no backing material. Low Q factor is associated with wide bandwidth. High Q factor is associated with low bandwidth. When we talk about Q factor, it is important to remember that the quality factor, or the Q factor, is the quality of the resonant frequency. So what do I mean by that? And this is going to be important because it's easy to think, well, Q factor is quality, and it's quality of a picture, right? No, it's the quality of the frequency being emitted by the probe. So remember, we had our 7 megahertz, no backing material, and we had our 5 megahertz transducer, lots of backing material. We had a low bandwidth. This one had a wide bandwidth. This one had a low Q factor. This one had a high Q factor. And that's because when the sound comes out of our 7 megahertz, it is going to be very close to a 7 megahertz wave coming out of it. It's going to be a very high quality 7 megahertz wave. That's what's coming out of it. Our 5 megahertz transducer with the backing material, remember we're going to get those little chirps that come out? These are going to be very low quality 5 megahertz waves because it has everything from 2 megahertz up to 8 megahertz in it. So that quality factor tells us how pure is the wave coming out of it, not how good the picture is. So high quality factor means a very pure frequency, and it's mostly associated with continuous waves which do not create pictures. Low quality factors are associated with transducers that have backing material that create short pulses. We know those short pulses create multiple frequencies, so low quality factors actually improve our images. I know that feels super backwards, but it's an important concept to understand again that our short pulses are there because of the backing material, and our short pulses improve our images, which has nothing to do with the quality factor of the wave coming out. The quality factor tells us that there's a wide bandwidth in relation to the main frequency. So kind of just to recap everything that we talked about, imaging transducers are more likely to have short pulses. They'll have backing material to create those short pulses. They end up having reduced sensitivity, wide bandwidth, and low Q factor because of that backing material. But with all of that, we get improved axial resolution. This is endgame right here. We want that resolution. Non-imaging transducers are going to have longer waves, longer pulses. They typically don't have backing material, and because they don't have backing material, they have increased sensitivity, a narrow bandwidth, and higher Q factor. But because they are non-imaging transducers, there's no image. So there's nothing really to speak of when we talk about image quality. All right, getting on to some other material that we just need to talk about a little bit more is the piezoelectric material. So we learned already that piezoelectric material is a man-made material typically for our transducers, and that it has this property, and when it has electricity applied to it, it'll create a sound wave, and then reverse is when that sound wave comes back, it'll create a voltage. PZT material typically is not naturally piezoelectric. It doesn't mean that if you found a rock, a quartz rock out in your rock garden or out in your yard, that you could hook up an electrode to it and create sound waves out of it. That's not what that means. Piezoelectric materials need to be polarized. And so what it means to polarize something, it means to heat the material while putting it in a strong electrical field. So the materials that become piezoelectric, there's materials that are capable of piezoelectric properties, but they have to be polarized to be able to express those properties. So again, polarization is heating the material while it's in a strong electrical field. The Curie temperature, which is also known as the Curie point, is the temperature to which we must get that PZT material heated to during polarization. So that high heat is the Curie temperature, and it must achieve Curie temperature while in that electrical field to become polarized. It is possible for our PZT materials to become depolarized. Depolarization happens if that PZT material is heated again to the Curie point, but is not within an electrical field. So again, when man-made PZT materials are made, they take the lead zirconate titanate material, they're going to heat it up to the Curie temperature while it's in an electrical field. That now creates our PZT materials as we know them so we can use them for ultrasound. If we were to take our transducer and heat it up to that Curie temperature, or take any sort of PZT material and heat it up to the Curie temperature while it was not within electrical field, it's going to depolarize and it's going to lose all of its piezoelectric properties. So if we heated up a transducer to extreme temperatures, it would no longer work. So that brings us to, how do we clean our transducers? Well, there's a couple different ways of cleaning materials like hospital items. Sterilization is kind of what we think about from when we think about hospital, right? We think about the sterile surgical room, we think about the sterile surgical instruments. Absolutely, those are made of materials that can be sterilized. And that's because sterilization is a process that's going to destroy every single microorganism. Nothing will be left. But the way that they do it is through extreme heat, chemicals, or radiation. And we just learned that we can't expose our transducer to extreme heat because it'll depolarize and no longer work. So we actually cannot sterilize our transducers. So what we end up doing is disinfecting them. Now, disinfection is a process where usually a chemical is applied to the transducer, and what it does is reduces the amount of microorganisms on the surface. So think about when you're scanning and we're done, we have those wipes. You clean off the top of your transducer. That reduces the microorganisms. It does not sterilize it. Now, a lot of the chemical wipes that we use are very good at killing viruses and a lot of infectious microorganisms, but it does not 100% get rid of everything like sterilization does. So that last little part was a little bit of a departure from what we've been talking about, but it does just kind of make us aware of how the piezoelectric material becomes piezoelectric, and then why we don't sterilize versus disinfect. All right, so we're going to kind of jump back into the physics side of things, and we're going to look at transducer frequencies. And we're going to look at then how the transducer frequency is created. So in continuous wave transducers, super simple. The electrical frequency that is applied through the wire to the piezoelectric material is the acoustic frequency. So a 7 megahertz volt is sent to the piezoelectric, 7 megahertz sound comes out. Pretty simple. Continuous wave, easy peasy, electrical frequency equals acoustic frequency. Pulse wave transducers, not as easy, but we can calculate it. So the frequency of sound that's produced by the pulse wave transducer is going to be determined by the PZT crystal. It's going to be determined by two things. How fast does the sound travel through the PZT crystal, and then the thickness of the PZT crystal. So let's first look at the speed of sound in the crystal. Now, we've been talking about speed of sound a lot. We know that 1.54 millimeters per microsecond is the constant of soft tissue speed of sound. Remember, speed of sound has everything to do with the material that it's traveling in. So the speed of sound in the PZT crystal is going to vary depending on what that PZT crystal, how that PZT crystal is made, what it's made of, and the acoustic properties of the crystal. So it's a little bit harder to give you a constant on that, but what we do know is that when the speed of sound through the PZT crystal is fast, we get a higher frequency. When the speed through the PZT crystal is slow, then we're going to have a lower frequency. So the speed of sound in the PZT crystal is directly related to the frequency. If speed increases, frequency increases. If speed decreases, then frequency decreases. The speed of sound again is fixed depending on how that PZT crystal is made, and we cannot change it. So when the manufacturers want to make a 5 megahertz transducer, then they make their PCT crystals so that it'll create a 5 megahertz sound. It's not something that we can go in and change. It is inherent to the transducer based on the way that it's made. The thickness of the PCT crystal then also helps to determine what that inherent frequency is. So when sound needs to travel through a thick PCT crystal, the frequency is low. When sound travels through a thin PCT crystal, the frequency is high. So now PCT is going to be, the thickness is going to be inversely related to frequency. More thickness equals low or less frequency. Less thickness is going to be high frequency. Again, it all has to do with how the element is made. The transducer manufacturer determines this. It is something that cannot be changed. Now, mathematically, there is a formula that goes along with what the frequency is, and I believe you'll have a little bit of practice of this in your workbook. This is not a formula that I would spend a lot of time remembering. Rather, understand the concepts that we are learning from this formula. So our formula tells us that frequency equals the speed of sound divided by 2 multiplied by the thickness. Okay, and it's speed of sound in the PCT. So again, don't spend a lot of time memorizing this. What you need to remember or need to understand are the relationships. When this part increases, frequency will also increase. These two are directly related. When this part increases, this is going to decrease. These two are inversely related. And we can just plug in some numbers just to kind of prove that part of it. So let's just say frequency equals, I'm just throwing numbers in just to show it. 10, we'll call our speed of sound, 2 times 5 as our thickness. We get 10 divided by 10. Frequency will equal 1 megahertz. Again, I'm just throwing numbers in just to kind of prove this. Let's see what happens then when we increase this. So now we've increased to 20. We now have 20 divided by 10. Frequency equals 2 megahertz. Let's increase this again to 30. Frequency equals 3 megahertz. So we can see as we increase the speed of our sound, we're going to increase our frequency. Now let's look back at changing the thickness. So let's start when it was 5. 30 divided by 10 gave us a frequency of 3 megahertz. Let's make this 10 now. 30 divided by 20, frequency equals 1.5 megahertz. So again, as this increased, our frequency started to decrease. So that formula just shows us what the relationships are and how to understand when one item increases, frequency also increases. When thickness increases, frequency decreases. It just helps us to understand those relationships. And that is the end of transducers. So the biggest part with transducers is going to be remembering all the components of the transducers, remembering what they do, and then out of this chapter, make sure that you really understand how the backing material affects the transducer, how bandwidth works, why Q factor is what it is and what it does, and then understand the concept that when the PCT crystal has certain speeds versus thicknesses, what that does to the frequency.